Hello everyone. Today we will talk about the normal distribution, and sometimes they call it the Gaussian distribution. It's one of the most important distribution in probability and statistics, and it explains and model many phenomena, and it is for a continuous random variable. So two things about the normal distribution. You need to know the mean and the variance or the standard deviation. So when you plot it, the x-axis here will be the different value for the random variable x. And the equation that describe this curve here, the probability density function, is this one. So you have the standard deviation of the random variable x, you have the mean of the random variable x, and if I plot this function for a specific value of mu and sigma, the standard deviation, for all possible values of x, you will get this curve. And the mathematical notation for a normal distribution of a random variable x is this one. And this is the two parameters you need, the mean and the standard deviation. And the normal distribution could be explaining the distribution of a resistor of an average value 100 ohm. So mu is 100 ohm. And the standard deviation sigma of 5 ohm. So 68% of the resistors will have values around the mean mu and one standard deviation to the right and one standard deviation to the left. So the area here under this curve will be 0.68. That means the portion of the resistors between this value and this value is 68% of the resistors in the population or manufactured by a machine. So mathematically, for example, if I want to find what is the probability that the random variable x is between mu minus sigma and less than mu plus sigma, then this will be the integral of the density function, this one, 1 over sigma 2 pi e minus x minus mu over 2 sigma square dx. And the integral will be from mu minus sigma from here to here, mu plus sigma. And if you evaluate this integral, you will get 0.68. You will get this value. Now, if I integrate from here, mu minus 2 sigma to mu plus 2 sigma, then I will get this area. And this area will come 0.95. So 95% of the resistor values will be around mu plus minus 2 standard deviation. Now the evaluation of this integral is not easy. You cannot evaluate it by hand. We use computer to do the evaluation or tables. We create tables to give us the values for different value of x. And if I want to find the probability that the random variable x less than a specific value, let's say x0, then I will integrate from minus infinity to x0 of this density function. And as we said, we cannot integrate these, so we create a table where here all possible value of x from minus infinity all the way to infinity for a specific sigma and mu. And here we will, in the table, list all probability. That means the area for x here, then this area, that will be a probability, then x this value, then this is the probability, for x this value, and this is the probability, and so forth. We list it in this table. And it will be for a specific sigma, a specific standard deviation. But that will be ridiculous, because we have different phenomena. It may be temperature and it's around 50 Fahrenheit, or sound pressure. So we cannot create these tables for every possible sigma and every possible mu for all kinds of different phenomena or variable we are studying. So the solution then is to standardize this normal distribution. So it will become the standard normal distribution. And what does that mean? It means the following. You will have any normal distribution with mu and the standard deviation, sigma. And that's the random variable x. Then I will do this transformation, create a new random variable, z, equal the random variable x minus mu, which is this, divided by the standard deviation, which is this one. And now this normal distribution will become a distribution like this, where the mean mu equals 0 and the standard deviation equal 1. So by doing this transformation, I can transfer any normal distribution with different value of mu and different value of sigma to this normal distribution with mu 0 and sigma 1. And now I can have only one table for this. And I can find the probability for z to equal or less any value. And that will be the same as the probability of x equal or less than any value of x of 0. So after I do this transformation and I found this probability, these two will be the same. Now mathematically we can show that. That's true. We can start with the probability x, the random variable less than x of 0. It's from minus infinity to x of 0, 1 over sigma 2 pi e minus x minus mu square over 2 sigma square dx. Now if I let z equal x minus mu over sigma, then when x goes to minus infinity, z will go to minus infinity. When x goes to x naught, z will go to x naught minus mu over sigma. And from here, dz will equal dx over sigma. Now I can explain this one probability. Instead of x, I will make it z less than x naught minus mu over sigma equal. Instead of the minus infinity here, it will be z minus infinity. Instead of x naught here, it will be this value, x naught minus mu over sigma. Now, this term will be e minus x minus mu here, x minus mu over sigma square. I will replace it by this one. That will be z square. Then I have these two here, over 2. And the dx here equal dz times sigma from here. Dx equal sigma dz. And then here 1 over sigma 2 pi. And this is minus infinity to x minus mu over sigma, or I can write it just z naught. 1 over this sigma will cancel this sigma, 1 over 2 pi square root e minus z square over 2 dz. And now this is the standard normal distribution. So f of z in this case is just 1 square root of 2 pi e minus z square over 2 with mean mu equals 0 and standard deviation equal 1. Now let's prove that. Is the random variable z has mu equals 0 and sigma equal 1? Well, we can prove it from this equation. If you have this equation and you have a random variable z related to the random variable x by this equation. So if I found mu of z, then mu of z will equal mu of x minus the mean of mu is just mu. It's just a constant divided by sigma. That's another constant. Now the mean of x is the same as mu because mu is the mean of x. So that will be mu minus mu over sigma, that is 0. Now to find the variance of z, let's rewrite this equation as z equal 1 over sigma x minus mu over sigma. Now the variance of z will equal, this is a constant, so I square it, 1 over sigma square, the variance of x. Now this constant never change, so the variance is 0. Then the variance of z equal 1 over sigma square times the variance of x. But the variance of x is just sigma square. These cancel this, and this is 1. So for a standard normal distribution, the probability density function is this. The mean is 0, and the standard deviation is 1. Now, if I plot these, it will look like this one, where the mean is 0. And if I go one standard deviation here equal 1, and I go 1 here, then the area here will be 0.68. And now I can calculate this integral using a computer for different value of z and tabulate that we will be using it in our quiz, in our test, in real life. And the table looks like this. These are all possible values for z. And if I want to find what is the probability z equal or less than minus 3.60, then I go to the table, I look, here is minus 3.6, I have 0 here, so that will be this one, 0. So I read this number and this number as minus 3.600. I read this number here and this number here as z equal minus 3.42, and so forth. So if I want to find what is the probability that z less than minus 3.17, I look, where is minus 3.1? That is minus 3.1. Then the 7 here will be this one. So I go in the table here, and that's the answer, 0.0008. So that's probably somewhere here, minus 3.17, and this is the area. Now, if I want to find what is the area probability z less than 0, well, z equal or less than 0 is here, so that will be this area. And we know this is half the area under the curve. But we can go down here until we found the 0, and that's the 0. That's the value of z, and it is 0.5. And that's how we read the table. Let's take another example. What if I want to find the probability z larger than minus 1.2 and less than 1.4? So this is the same as probability z less than 1.4 minus the probability z less than minus 1.2. If I plot it here, this is z and this is 0 here. I'm asking for the probability minus 1.2. Let's assume it is somewhere here, and 1.4. It's somewhere here. So I am asking for this area. It is the same as the probability z less than 1.4. So that means all this area here minus the probability z less than 1.2. Minus 1.2 is here, minus this area. So if I take the blue area minus the green area, I will get the desired probability, which will be this one. And I can find this from the table as follows. What is the probability z less than 1.4? So I go in the table and I look for 1.4. That's 1.40. So this is this one, 0.9192. So this one is 0.9192 minus the probability z less than minus 1.2. Minus 1.2 is here, 0.1151. And if I subtract these, I should get 0.8041. And that's how we find the probability for a normal distribution. Remember, we first convert any distribution to a standard normal distribution. Then we use the table. Otherwise, if you have a software or a program that can find the probability for any sigma and mu, then you can work with that. Okay, let's do some examples. Aluminum sheet used to make beverage cans have thickness in thousandths of an inch that are normally distributed with mean 10 and standard deviation 1.3. So the mean is 10 and standard deviation of 1.3. A particular sheet is 10.8 thousandth of an inch thick. Find the z-score. The z-score mean how do I convert x to a z, standardized. So then z equal x minus mu divided by sigma. X is 10.8 minus the mean, which is 10, divided by the standard deviation, which is 1.3. So this is 0.61538. So if I plot the z standard normal distribution, where this is the 0, then this 10 will be mapped to here, and the 10.8 will be mapped to 0.6, which is somewhere here. So that 10.8 will be mapped to here. Then I can use the normal standard table to find any probability. And they want to find what is the original unit in inch. So they gave us z and they want to find what is x. So we plug here minus 1.7 equal x is unknown, minus mu is 10, divided by the standard deviation, which is 1.3. So solving this equation, you will find x equal 7.79. So that's the original thickness of the sheet. We already talked about how do we find area under the normal curve and using the table. So let's just move on and take this example. Here is a standard normal distribution. This is 0, and they want the area to the left of z. So z is here, and it's 0.47. So basically they want the probability z equal or less than 0.47. So we want to find this area. Well, we can go to the table and we look for 0.47 and find that area. So let's go to the table. 0.47, that's 0.4. Now we look for here, 0.07. So that is 0.47. This 2 is 0.47. So the area will be this one, 0.6808. Find the area under the curve to the right of z equal 1.38. So now they want the probability of z larger than 1.38. So z probably here, 1.38, and they want this area. So to solve this problem, the table will always give me less than z. So I can use the table to find this area, then subtract it from 1 will give me the desired area here. So this is the same as the probability, this is the same as 1 minus the probability z less than 1.38. And if I use the table, z less than 1.38 is here. This is 1.3 and 8 is here. So I go down here, and that is the probability, 0.9162. So this is 0.0838. And that would be the area of this part. Let's do the final one here. Find the area under the normal curve between z 0.71 and z 1.28. So I want to find this area, 1.28 and 0.71. So that is the probability z larger than 0.71 and less than 1.28. And this is the same as the probability z less than 1.28 minus probability z less than 0.71. Remember, the table only gives the area to the left of the z value. So basically, graphically, that means I'm gonna find this area first, which is this one, and then find this area, the green one, which is this one, and subtract the green area from the red area. That will give me the blue area, the area between 0.71 and 1.28. And if I use the table to look for probability z less than 1.28 and z less than 0.71, that will be this one, 0.8997 minus probability less than 0.71 is 0.7611. And if I calculate these, I should get 0.1386. So let's look at this example. A process manufactures ball bearing whose diameters are normally distributed with mean 2.505. Mu equal 2.505 centimeter and the standard deviation 0.008 centimeter. Specification call for the diameter to be in the interval 2.5 plus minus 0.01 centimeter. What proportion of the ball bearing will meet the specification? So if we plot these, the mean is 2.505. So they are interested in ball bearing not less than 2.5 minus 0.01, so that is 2.49, and not more than 2.5 plus 0.1, so that is 2.51. So they want this probability, this area. Well, we're gonna standardize this x random variable. So this is x. So if I have x here and z here, so when x is 2.49, z will be x minus mu divided by the standard deviation. So when x is 2.49, minus mu is 2.505 divided by sigma 0.008, so this value equal minus 1.875. Now let's find the maximum value of x. What is it in terms of z? So that means this will be 2.51 minus 2.505 over 0.008, and this will be 0.625. So the desired probability, which is the red area here, is equivalent to the following. This normal distribution with z here, and I need to find the area under minus 1.875 and 0.625. So I want to find this green area. And this green area will be equivalent to the red area because this is mapped to here, this is mapped to here. Now I can use the table and find what is the probability. So probability x larger than 2.49 and less than 2.51 is the same as the probability z larger than minus 1.875 and less than 0.625. And if I do it in the table, let's look at the probability minus 1.87. So minus 1.8 is here, 7 somewhere here. So that is minus 1.87. But our is minus 1.875. So it is the number going to be between 0.07 and this number, 0.07 and 0.08. That will be between these, minus 1.88. So I can approximate it to be 0.0305. So I can approximate it to be between these two numbers. So it will be, this will be 0.0304. Now let's look for 0.625. 0.6 is here, 2 is here, So this is 0.62, but it is 0.625. So 0.63 is here, so it's gonna be between these two numbers. So then this will be 0.733. Okay, so we go back to our problem, and we said this is the same as probability z less than 0.625 minus probability z less than minus 1.875. And this probability from the table, we find it 0.733, and this probability we found it to be 0.0304, and this is 0.7026, which is close enough to this. It depends on the approximation. If you use a computer, it will give you the answer perfectly. In estimating the parameters of a population, now let's assume we have a population here, and this could be an outcome of many measurements or parameters of a device. And these measurements here, or outcomes, they follow a normal distribution with mean mu and a variance sigma square. But you don't know mu, you don't know the standard deviation of the population. So you take a sample of good size and you estimate mu with the sample mean x, which is x1 plus x2 all the way to xn, the size of the sample. And the uncertainty in this estimate will equal the standard deviation of the sample divided by square root of n, and we showed that in previous slides. If you have the standard deviation of the population, then you replace it by the actual standard deviation of the population. But usually we don't have it, so we use the standard deviation of the sample here we took. Now, if I have a new random variable in terms of the random variable x, so let's call this z, then z will also have a normal distribution, but the mean of z will be this, a, this constant, times the mean of x plus the constant. And the variance of the random variable z will be a squared times the variance of x, a squared times the variance of x. And we showed this when we discussed the discrete random variable. Now, if I have many random variables, x1, x2, xn, and they are independent, and they have a normal distribution with mu1 for x1, mu2 for x2, and mu_n for xn, and that's the variance of x1, x2, and xn. If I sum all these variables that have normal distribution, then the sum will also have a normal distribution. And the mean of all the sum will be this one, which is C1, the mean of x1, plus C2, the mean of x2, plus Cn, the mean of xn. And the variance of the sum of all these random variables will be C1 squared times the variance of x1 plus C2 squared times the variance of x2, and so forth until the Cn. So the sum of many random variables that are independent and they have a normal distribution, the sum will also have a normal distribution with this mean, which is the sum of the means, and the sum of the variance of each random variable. Let's take this example. A chemist measured the temperature of a solution in centigrade. The measurement is denoted by C and is normally distributed with mean 40 and standard deviation 1 centigrade. Now the measurement is converted to Fahrenheit. What's the distribution? Well, Fahrenheit now will have a normal distribution with mean equal 1.8, the constant, times the mean of the centigrade, plus the constant 32. And the variance will be the constant squared times the variance of C. Now the constant doesn't affect the variance because it will be added to every parameter, so no variation. And this will be a normal distribution. The mean of the centigrade is 40, so 40 times 1.8 plus 32 is 104. And the variance will be 1.8 squared times the variance of C, which is 1 centigrade squared, that is 3.24 Fahrenheit. Now let's look at distribution of functions of normal distribution. And this one we already talked about. If I have a sample and I have many random variables here, and I took a sample of size n, and then I created this new random variable, which is the sum of x1 plus x2 plus xn. Now x bar will have a normal distribution with mean the same mean as the population, or the same mean as each of these random variable, and the variance will be sigma square over n, and sigma square is the variance of the population. So now the sample mean is a random variable that follow normal distribution with average mu and a variance, this one. Now if I have two separate random variable and they are independent, with x is a normal distribution with mean mu x and the variance sigma x squared, and the random variable y also follow a normal distribution with mean mu y and the variance sigma squared y. If I add them, then the mean will be mu x plus mu y, and the variance will be the sum of the variance of x and y. If I subtract them from each other, the mean will be mu x minus mu y, but the variance will be the same. It's just the variance of x squared plus the variance of y squared. And again, when we discussed the discrete random variable, we showed this property is true. Okay, I will stop here, and in the next video we will talk about the exponential and other distributions. Thank you for watching, and see you in the next video.